In a tunnel 100 meters beneath the border of France and Switzerland, a machine built to answer the oldest question in physics found something it was never designed to explain. Physicists at CERN were hunting for one particle in 2012, and they found it. But buried inside the debris of that discovery was a number that should not exist, a value so finely balanced that if it were different by the smallest imaginable fraction, atoms would never have formed, and no version of reality could exist to notice. That number has never been explained. It has not gone away. It has only been joined, year after year, by stranger numbers, by particles that flicker into existence and then vanish from the data, by measurements from different corners of the same machine that refuse to agree with each other, and by a persistent, nagging signal that some of the best physicists on the planet believe may be the first crack in the deepest theory science has ever built. This is why a machine built to confirm the universe we know keeps returning results that suggest we do not know it at all. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath, and let's begin. The Large Hadron Collider was never supposed to be controversial. It was built as a confirmation machine. By the middle of the 2000s, physicists had spent half a century assembling a theory called the Standard Model, a mathematical framework describing every known particle and every known force except gravity. The model predicted the existence of a particle that had never been seen, a field thought to fill all of space and give mass to everything that has mass. Without it, electrons would weigh nothing, atoms would never form, and stars, planets, and every living thing would be impossible. The particle was named after the physicist who first described the mechanism, Peter Higgs, though 5 other theorists arrived at similar ideas around the same time. For decades, the Higgs boson existed only on paper, a placeholder in equations that worked beautifully everywhere else. Finding it required smashing protons together at energies never before achieved by human engineering. Then sifting through the wreckage for a particle that would appear for less than a billionth of a second before disintegrating into other particles that could actually be detected. The Large Hadron Collider was built for exactly this purpose. A ring 27 kilometers in circumference, cooled to a temperature colder than deep space, accelerating protons to within a hair's breadth of the speed of light and smashing them together roughly 40 million times each second. 2 enormous detectors, called Atlas and CMS, watched the collisions independently, built by separate teams, using separate methods, specifically so that neither could bias the other's results. On the 4th of July in 2012, both detectors announced they had found it. A new particle, weighing about 133 times the mass of a proton, appearing in exactly the ways the Higgs mechanism predicted. The room in Geneva erupted. Peter Higgs, sitting in the audience, wiped away tears. Newspapers around the world ran the story on their front pages, and physicists spoke of completing the Standard Model, of finally closing the book on nearly a century of theoretical work. But even as the applause continued, a smaller group of theorists in the same building were doing something else entirely. They were staring at the mass of the newly discovered particle and asking a question that had nothing to do with celebration. Why is it that number? Not roughly that number, not approximately that number, but precisely, exactly, to a level of fine-tuning that made several senior physicists visibly uncomfortable during the announcement itself. The Higgs boson's mass is not simply a fixed constant handed down by nature. According to the mathematics of quantum field theory, the mass of the Higgs should be dragged upward by interactions with every other particle it touches, including hypothetical particles at energies far beyond anything the Large Hadron Collider can reach. Left unchecked, those quantum corrections should push the Higgs mass up toward energies close to the Planck scale, the energy at which gravity itself becomes as strong as the other forces, a number so enormous it dwarfs anything measured in the collider by many orders of magnitude. For the Higgs to weigh what it actually weighs, something has to cancel those corrections almost perfectly, to a precision of about 1 part in 10,000 trillion. Nothing in the standard model explains why that cancellation happens. It simply does, as if by extraordinary coincidence. Physicists call this the hierarchy problem, and it has haunted the field since long before the Higgs was ever found. There are only a few ways to explain a coincidence that precise. Either there is a deeper symmetry in nature that forces the cancellation to happen automatically, some elegant mathematical structure not yet discovered, or the universe is one of an almost unimaginable number of possible universes, each with different fundamental constants, and we happen to exist in one of the rare ones where the numbers work out, simply because only in such a universe could anyone exist to ask the question. Or there is something else entirely, some idea nobody has had yet, waiting in the data that the Large Hadron Collider has already collected. The leading candidate for that deeper symmetry was a theory called supersymmetry, and it made a very specific promise. If supersymmetry were true, then every particle in the standard model should have a heavier partner particle, a superpartner, and the quantum corrections from ordinary particles would be almost exactly cancelled by corrections from their superpartners. It was mathematically elegant. It solved the hierarchy problem cleanly. It also, as a remarkable side benefit, predicted the existence of a stable, weakly interacting particle that could account for dark matter, the invisible substance that outweighs ordinary matter in the universe by more than 5 to 1. For 3 decades, supersymmetry was the most popular idea in theoretical physics, and thousands of papers were written exploring its consequences. The Large Hadron Collider was built partly to find it. If supersymmetric particles existed at the energies physicists expected, the machine should have seen unmistakable evidence within its first years of operation. It did not. Run after run, search after search. The collider has found no supersymmetric particles at all. The simplest and most elegant versions of the theory have been ruled out entirely. More complicated versions survive, but only by pushing the predicted particles to higher and higher masses, further and further from where they were supposed to be found, in a pattern that many physicists describe uncomfortably as retreating rather than confirming. The clean solution to the hierarchy problem has not been found, and so the crack remains exactly where it was in 2012. A number that should not be what it is, sitting at the heart of the particle that gives the universe its mass, unexplained and unresolved more than a decade after its discovery. This was the first crack. It would not be the last. 3 years after the Higgs announcement, something else appeared in the data, and for a few months in late 2015, it looked like physics might be about to break wide open. Both ATLAS and CMS, the same 2 independent detectors that had confirmed the Higgs, began seeing an unusual excess of events in which 2 photons emerged from a collision, carrying a combined energy corresponding to a mass of about 800 times the mass of a proton. Nothing in the standard model predicts a particle at that mass decaying that way. If real, it would have been a genuinely new fundamental particle, something outside the theory entirely, the first confirmed crack in the standard model since its completion. The excitement inside the physics community was almost impossible to overstate. Within weeks, theorists had written more than 500 papers proposing explanations for what the new particle might be. Some suggested it was a heavier cousin of the Higgs. Others proposed it was evidence of extra dimensions of space curling up at scales the collider could finally probe. Some connected it to dark matter, others to entirely new forces of nature nobody had previously considered. Conferences were reorganized around it. Graduate students switched thesis topics to chase it. The excess appeared with a statistical significance that, while not yet meeting the formal threshold physicists require to claim discovery, was tantalizingly close, hovering for a period at a level that historically has often, though not always, turned into something real. The threshold physicists use to distinguish a genuine discovery from a statistical fluctuation is called 5 sigma, meaning the odds that the observed pattern arose purely by chance are smaller than about 1 in 3.5 million. Anything below that is treated as interesting but unconfirmed. The bump was never far off, sitting for a time at a significance that made it the most talked about anomaly in a generation. Then, in the summer of 2016, both detectors collected a much larger sample of collisions, 4 times the previous amount, enough to settle the question decisively. The bump disappeared. It had been what physicists call a statistical fluctuation, a chance clustering of ordinary events that mimicked the signature of a new particle purely by accident. With enough new data, the illusion washed out, and the excess simply was not there anymore. The collapse of the diphoton bump became something of a cautionary tale within particle physics, a reminder of how tempting it is to see structure in noise, and how essential it is to wait for enough data before believing a discovery is real. It also revealed something less discussed but arguably more important: a genuine tension in how modern physics operates. The field has built extraordinarily powerful statistical tools for filtering out false signals, yet the very act of searching across thousands of possible mass values and decay patterns means that somewhere, purely by chance, a few of those searches will produce results that look compelling before more data reveals them to be nothing. The diphoton bump was not evidence of new physics, but it was evidence of something else. The razor-thin line researchers walk between genuine discovery and self-deception, and how easily an entire field can convince itself that a crack has appeared, only to watch it seal itself shut months later. Yet even as physicists absorbed that lesson, a different kind of anomaly was quietly accumulating in a completely different corner of the same machine, one that would take years longer to test, and whose fate would turn out to be far more complicated than a single bump that simply vanished. That anomaly lived inside the LHCb experiment, a detector purpose-built not to hunt for brand-new particles directly, but to study the decays of particles containing a heavier cousin of the ordinary quarks that make up protons and neutrons, a particle called the beauty quark. Beauty quarks are unstable, and they decay in numerous ways, but the Standard Model makes an unusually precise and testable prediction about certain of those decays. It predicts that when a particle containing a beauty quark falls apart into a pair of leptons, the theory should not care whether those leptons are electrons or their heavier cousins, muons. Aside from a tiny, calculable difference caused by their different masses, the 2 decay channels should occur at almost exactly the same rate. This principle is called lepton universality, and it sits close to the foundation of the entire theory, a statement that the forces of nature treat the different types of leptons identically except for their mass. Beginning in 2014 and continuing for the better part of a decade, LHCb researchers began measuring the ratio between these 2 decay channels, a quantity physicists call R sub k, and later a related quantity called R sub k star. If the Standard Model is complete, this ratio should equal almost exactly 1. Instead, measurement after measurement returned a ratio noticeably below 1, meaning beauty quarks appeared to be producing electron pairs more often than muon pairs, in apparent violation of one of the theory's core assumptions. The deviation grew slowly, more significant, as more data accumulated, eventually reaching a level of about 3 standard deviations, not yet enough to claim discovery under the strict 5 sigma standard, but persistent, repeated, and showing up consistently across multiple independent analyses using different decay channels. What made the anomaly especially tantalizing was that it did not appear in isolation. Several related measurements, involving similar beauty, quark decays, and similar comparisons between different types of leptons, showed deviations pointing in a broadly consistent direction. Theorists began constructing what are called global fits, mathematical frameworks combining dozens of individual measurements to test whether a single new phenomenon, rather than several unrelated coincidences, could explain the whole pattern. Remarkably, such unified explanations worked. Entire classes of hypothetical particles, including something called leptoquarks, particles that would allow direct transformation between quarks and leptons, were proposed specifically to explain the pattern. For years, this collection of anomalies was treated by a significant portion of the theoretical community as the most promising hint of new physics anywhere in collider data. More credible in many physicists' eyes than the Diffeton bump had ever been, because it was not one bump in one experiment but a slowly building, cross-checked pattern spread across years of careful measurement. Then, in December of 2022, LHCb released its most precise measurement yet, using its complete dataset and an improved analysis technique. The result matched the standard model prediction almost exactly. The 3 sigma deviation that had persisted for the better part of a decade had evaporated. Follow-up measurements in the years since, including refined analyses published through 2025, have continued to confirm the agreement, extending the test into new mass ranges with even greater precision. The particle physics community, which had spent years constructing elaborate theoretical frameworks to explain the deviation, was left with what one researcher publicly described, with evident disappointment, as another confirmation of the standard model rather than the new discovery so many had hoped for. It would be easy to read this as a second cautionary tale, another crack that turned out to be an illusion once enough data accumulated, much like the Diffeton bump before it. And in the specific case of R sub k and R sub k star, that reading is correct. But this particular story does not end there, because within the very same family of beauty quark measurements, a separate and structurally different test of lepton universality has behaved in exactly the opposite way. Rather than fading as more data arrived, it has grown more persistent, and as of the most recent global analyses, it remains one of the most stubborn tensions in the entire field. This other measurement compares decays of beauty quark particles into a heavier and much less common lepton, the tau, against decays into lighter leptons. The relevant quantities carry the names R sub d and R sub d star, and they test the same principle of lepton universality, but through a different mechanism than the one that produced the vanishing R sub k anomaly, where R sub k involves a rare quantum process, occurring only through complicated indirect pathways, sometimes drawn as tiny, looping diagrams. The R sub d measurements involve a much more common, directly occurring decay. This matters because it means the two anomalies, despite sounding similar, are testing fundamentally different aspects of the theory, and a resolution of one has no direct bearing on the other. Multiple experiments, including the Bobber collaboration in California, the Bell and Bell 2 collaborations in Japan, and LHCb at CERN, have each independently measured R sub d and R sub d star. Every single one of them has found values above the standard model prediction. Not equal, not consistent with statistical noise scattered randomly around the predicted value, but each experiment landing on the same side of the prediction, again and again, across different detectors, different analysis teams, and different decades of data collection. When researchers combine all of these independent results into a single world average, as an international collaboration of theorists did most recently in an extensive analysis published in 2024, the combined deviation from the standard model prediction sits at a level of roughly 3.5 standard deviations, and the updated global picture, incorporating the newest LHCb and Bell 2 results, continues to favor a genuine violation of lepton universality between tau leptons and their lighter cousins. 3.5 standard deviations is not yet a discovery. Physicists have seen deviations at this level before that eventually resolved into nothing, and history, including the story of R sub k itself, counsels caution. But the R sub d anomaly has a different character than either of the two anomalies already discussed. It has not spiked and vanished like the diphoton bump. It has not slowly built and then evaporated with a single decisive measurement like R sub k. Instead, it has persisted, essentially unchanged in significance, across nearly a decade of independent measurements from separate experiments using separate methods, none of which have found a way to make it disappear. Every new dataset that arrives adds to the tension rather than resolving it. Theorists have proposed several explanations, most of them involving new particles that interact differently with tau leptons than with electrons or muons, a natural consequence of the tau's much greater mass, which makes it more likely, in some theoretical frameworks, to couple strongly to whatever new physics might exist. Leptoquarks appear again in these models, as do certain extended versions of the Higgs sector, involving multiple Higgs-like particles, some of which would also help explain the unresolved hierarchy problem discussed earlier. None of these models has been confirmed, and none is universally accepted among theorists, some of whom continue to argue that subtle, difficult-to-calculate effects within the standard model itself, involving the complex internal structure of the particles undergoing these decays, could eventually account for the entire discrepancy without requiring any new physics at all. What makes this anomaly worth taking seriously is not any single measurement, but the shape of the pattern across time. A statistical fluctuation, by definition, should regress toward the true value as more data accumulates. The R sub d anomaly has not done that. It has sat in roughly the same place, measurement after measurement, experiment after experiment, for the better part of a decade, refusing either to strengthen into an undeniable discovery or to fade into agreement the way its cousin ultimately did. Bell 2, still actively collecting data in Japan, and the ongoing Run 3 of the Large Hadron Collider are both expected to sharpen this measurement considerably over the coming years. Whether it finally crosses the 5 sigma threshold that would mark it as a genuine discovery, or whether it slowly dissolves the way R sub k did, remains one of the most closely watched open questions in the field. For now, it stands as a real, unresolved, and stubbornly persistent crack. Not every crack in the standard model has come from inside the tunnel at CERN. Across the ocean, at Fermilab outside Chicago, a separate experiment spent the better part of a decade chasing an anomaly that, for a while, looked like it might be the clearest evidence yet that the standard model was incomplete, and its story is deeply intertwined with the theoretical work being done by physicists at CERN itself. The experiment measures a property of the muon, the heavier, unstable cousin of the electron, called its magnetic moment, a number describing how the particle behaves like a tiny spinning magnet when placed inside a strong magnetic field. Quantum theory predicts this value with extraordinary precision, because the muon's magnetic moment is influenced by every other particle in existence, popping in and out of existence around it for fleeting moments, as what physicists call virtual particles. If an undiscovered particle exists anywhere in nature, its fleeting presence should very slightly shift the muon's magnetic moment away from the Standard Model's prediction. An earlier experiment at Brookhaven National Laboratory in the late 1990s and early 2000s first measured a magnetic moment that differed from theoretical predictions at the time. The result was intriguing but not decisive enough to draw firm conclusions. 2 decades later, the same physical apparatus, an enormous superconducting magnetic ring, was transported in one piece from New York to Illinois in a journey that made headlines purely for its engineering complexity, so that Fermilab could repeat the measurement with far greater precision. The first results, announced in 2021, agreed closely with the earlier Brookhaven measurement and appeared to confirm a real deviation from theoretical predictions, sending a wave of excitement through the physics community that lasted for years. Combined, the two experimental results disagreed with the theoretical prediction available at the time by more than 4 standard deviations, tantalizingly close to the 5 sigma line that separates a curiosity from a confirmed discovery. But this anomaly had a peculiar feature that set it apart from every other crack discussed so far. The tension was not simply between one clean experimental number and one clean theoretical number. It was between an experimental measurement that kept becoming more precise and a theoretical prediction that turned out to be far harder to calculate reliably than anyone had expected. The dominant source of difficulty involves what physicists call hadronic contributions, complicated effects arising from the strong force binding quarks together, which cannot be calculated directly from first principles the way most of the rest of the prediction can. 2 different methods for estimating these contributions, one based on translating real experimental data from electron-positron collisions, the other based on massive supercomputer simulations called lattice quantum chromodynamics, began producing noticeably different answers from each other, even before comparing either one to the Fermilab measurement. An international collaboration of theorists, drawing on expertise from CERN and dozens of other institutions around the world, spent years working to resolve which of these theoretical methods was more reliable. In the spring of 2025, they published an updated calculation relying more heavily on the lattice approach, and the new theoretical prediction shifted substantially, landing much closer to the experimental value. Weeks later, in June of 2025, Fermilab released its own final, most precise measurement of the muon's magnetic moment, achieved after years of refining the experiment's muon beam and reducing sources of error. The final experimental number agreed closely with the earlier Fermilab results. But when compared against the newly revised theoretical prediction, the anomaly that had captivated physicists for years was largely gone. The gap between experiment and theory had closed, not because the experimental measurement changed, but because the theoretical prediction moved to meet it. This resolution, unlike the clean collapse of the Diffeton bump, revealed a crack in a different place entirely, not between experiment and theory, but within theory itself, between 2 competing methods of calculation that still disagree with each other at a level of about 3 standard deviations. The muon magnetic moment puzzle, largely settled as a test of new physics, has left behind an unresolved question about the reliability of the tools physicists use to make predictions in the first place. In science, closing one gap sometimes only reveals the shape of another gap, hiding directly behind it. The W boson mass tells a similar story, but with a resolution that has never actually arrived. The W boson is one of the particles responsible for carrying the weak nuclear force, the force behind radioactive decay, and its mass is one of the most precisely predictable quantities in the entire Standard Model, tightly constrained by its mathematical relationship to the mass of a related particle called the Z boson. along with the strengths of the electromagnetic and weak forces. Get any of those relationships slightly wrong, and it signals the presence of something the theory does not account for. In April of 2022, the CDF collaboration, working with data collected over more than 2 decades at the now-retired Tevatron Collider at Fermilab, released a new measurement of the W boson's mass. The results stunned the field. It disagreed with the standard model prediction by roughly 7 standard deviations, an enormous discrepancy by the standards of particle physics, and far beyond the 5 sigma threshold normally required to claim a discovery. Had it held up, it would have been one of the most significant results in the history of the field, clear evidence of new particles or forces beyond anything currently known. Within days, hundreds of theoretical papers appeared, proposing explanations, connecting the anomaly to nearly every open puzzle in physics, including, in some proposals, the very same lepton universality anomalies and the muon magnetic moment tension discussed earlier, in an attempt to find one elegant new theory that could explain all of the anomalies at once. The response from the rest of the field was immediate scrutiny. Every other precision measurement of the W boson's mass, made by entirely different collaborations using entirely different detectors and entirely different techniques, had found values consistent with the standard model prediction, though generally with less precision than CDF claimed to have achieved. This included measurements from the LHCb detector and from ATLAS at CERN, the same detector that had helped discover the Higgs boson a decade earlier. In the years following the CDF announcement, ATLAS revisited its own earlier analysis using improved techniques and achieved a substantially more precise result, one that remained solidly consistent with the standard model and increasingly in tension with the CDF value. The CMS collaboration at CERN released its own new measurement in 2024 using an entirely independent method, and it too landed close to the standard model prediction, nearly matching CDF's precision while disagreeing with CDF's central value. What makes this anomaly genuinely strange, rather than simply a single outlier waiting to be explained away, is that the CDF collaboration has stood firmly behind its result. Rather than retracting or softening the claim under pressure from conflicting measurements elsewhere, CDF researchers have continued to defend their analysis, addressing specific technical criticisms raised by outside physicists point by point and reaffirming their original number. The disagreement, more than 4 years after it first appeared, has not been resolved. It remains. Structurally, one measurement, standing 7 standard deviations from theoretical expectation, surrounded by several other measurements from different experiments that agree closely with each other and with the theory, but not with CDF. A working group, combining measurements from across the LHC and the Tevatron, continues to study how, or whether, these results can be reconciled at all. This is a different kind of crack than any discussed so far, not a signal that appeared and vanished, and not a tension that gradually resolved as theory and experiment converged. It is an isolated, stubborn disagreement between one exceptionally careful measurement and everything else physicists have measured about the same quantity, with the scientists who produced the outlier declining to walk it back. Whether it eventually turns out to reflect some subtle, undiscovered systematic error in the analysis, or whether it is quietly pointing toward physics beyond the standard model that other experiments have simply not yet been sensitive enough to detect, nobody currently knows. It remains one of the strangest open threads in modern particle physics. Underlying every one of these individual anomalies is a much larger crack, one so enormous that physicists sometimes forget to mention it precisely because it has been sitting there, unresolved, for so long. The standard model, for all its success at describing the Higgs boson, the beauty quark, the muon, and every other particle ever produced in a laboratory, describes only a small fraction of the universe's total contents. Detailed observations of galaxies, galaxy clusters, and the faint afterglow of the early universe all point to the same conclusion. Roughly 5 times more matter exists in the cosmos than all the ordinary matter made of protons, neutrons, and electrons combined. This invisible material, called dark matter, does not emit, absorb, or reflect light. Its presence is inferred entirely through its gravitational pull on the things that do. For decades, the leading hypothesis held that dark matter consists of a new type of particle, one that interacts with ordinary matter only through gravity and the weak nuclear force, making it exceptionally difficult to detect directly, but not impossible. These hypothetical particles, generically called weakly interacting massive particles, were exactly the kind of things supersymmetry predicted, and building a machine capable of producing them at high energy was one of the central justifications for constructing the Large Hadron Collider in the first place. If dark matter particles exist at the energies favored by the simplest theoretical models, collisions inside the machine should occasionally produce them directly, and physicists would see the telltale signature of energy and momentum disappearing from a collision, carried away by particles the detectors cannot see. That signature has never appeared. Across more than a decade of searches, spanning both the ATLAS and CMS detectors and covering ever-expanding ranges of possible dark matter particle masses and interaction strengths, no convincing evidence of a dark matter particle has been found at the Large Hadron Collider. Each null result narrows the space of possible theories a little further, ruling out entire categories of models that seemed promising a decade ago. Dedicated dark matter detection experiments deep underground, shielded from cosmic radiation by kilometers of rock, have conducted parallel searches using entirely different techniques, watching for the extraordinarily rare event of a dark matter particle striking an atomic nucleus directly. These experiments too have returned null results, again and again, steadily eliminating the simplest and most natural candidates. The combined effect of these repeated null results across the collider, underground detectors, and astronomical observations has left the field in an uncomfortable position. The evidence that dark matter exists somewhere in the universe remains as strong as ever, drawn from multiple independent lines of astronomical observation that continue to reinforce each other. But the leading theoretical explanation for what dark matter actually is, a weakly interacting particle within reach of current experiments, has failed every test designed to confirm it. Physicists have responded by broadening their search, considering far lighter or far heavier candidate particles. Entirely different categories of dark matter involving primordial black holes or exotic field configurations, and modifications to the theory of gravity itself, though this last category remains a minority position, difficult to reconcile with the full range of astronomical evidence. The crack here is not a single anomalous measurement. It is an entire category of matter, 5 times more abundant than everything visible in the night sky, sitting completely outside the standard model, waiting for an explanation that no experiment has yet provided. There is a second gap of similar magnitude, quieter than dark matter in public conversation, but no less troubling to the physicists who study it, and it concerns the simple fact that anything exists at all. According to the standard model, the earliest moments after the beginning of the universe should have produced matter and antimatter in exactly equal amounts. Every particle of ordinary matter has an antimatter counterpart, identical in mass but opposite in electric charge. And when a particle meets its antiparticle, both annihilate in a burst of energy, leaving nothing behind. If the early universe truly created matter and antimatter in perfectly equal quantities, then as the cosmos cooled and expanded, virtually everything should have annihilated, leaving behind a universe filled with light and almost nothing else. No stars, no planets, no observers to wonder about any of it. Clearly, that did not happen. For every roughly 1 billion pairs of matter and antimatter particles produced in the early universe, physicists calculate that there must have been one extra particle of matter with no antimatter counterpart to annihilate against. That tiny surplus, roughly 1 part in a billion, is the entire reason anything exists today. Every galaxy, every star, every planet, every person, built from the leftover imbalance after nearly everything else destroyed itself. The Standard Model does contain a mechanism that treats matter and antimatter slightly differently, a phenomenon called charge parity violation. First observed experimentally in the 1960s and studied intensively since. LHCb was specifically designed, among other purposes, to measure this effect with extraordinary precision in the decays of particles containing beauty quarks, and it has succeeded in observing charge parity violation in numerous different decay channels, providing some of the most precise tests of the phenomenon ever conducted. The trouble is a matter of scale. The amount of charge parity violation built into the Standard Model, even after accounting for every measured instance of it, is many orders of magnitude too small to explain the actual imbalance between matter and antimatter observed in the universe. Physicists have calculated this discrepancy carefully, and depending on the precise assumptions used, the Standard Model falls short of explaining the observed matter-antimatter asymmetry by a factor of roughly 10 billion or more. Something else, some additional source of asymmetry entirely outside current theory, must have operated in the earliest fractions of a second after the universe began, tilting the balance just enough to leave behind the matter that makes up everything we can see and touch. This is, in a sense, the oldest and largest crack of all, one that has nothing to do with a specific anomalous measurement and everything to do with the plain fact that a universe governed only by the known laws of physics should not contain any matter whatsoever, and yet unmistakably does. LHCb continues to search for new, undiscovered sources of charge parity violation in ever more exotic particle decays, hoping to find some additional mechanism operating beyond the Standard Model that could account for the missing asymmetry. So far, every new decay studied has continued to behave within the violations already known, exactly as expected. The imbalance that allowed the universe to exist remains unexplained, sitting quietly beneath every other anomaly discussed so far, the deepest and most fundamental crack of them all. A different kind of crack came not from a collider at all, but from experiments watching a particle so light and so elusive that for decades physicists assumed it had no mass whatsoever. Neutrinos are produced in staggering numbers by the sun, by nuclear reactors, by cosmic rays striking the upper atmosphere, and by the reactions inside every star that has ever burned. Trillions of them pass through every person's body every second without any noticeable interaction at all, because neutrinos interact with ordinary matter so weakly that a wall of lead, a light year thick, would stop only about half of the neutrinos passing through it. In the original formulation of the Standard Model, neutrinos were assumed to be exactly massless, a clean theoretical simplification with no obvious contradiction from any experiment available at the time. Beginning in the late 1990s, experiments watching neutrinos produced by the sun and by cosmic rays hitting the atmosphere discovered something the massless assumption could not explain. Neutrinos come in 3 distinct types, tied to their association with the electron, the muon, and the tau. Detectors, built to count how many electron-type neutrinos arrive from the sun, consistently found roughly 1/3 the expected number. a persistent shortfall that puzzled physicists for years and was known as the solar neutrino problem. The resolution turned out to be strange and beautiful. Neutrinos do not travel through space as a fixed type. They oscillate, shifting between the three types as they travel, a quantum mechanical phenomenon that can only occur if neutrinos possess mass, however small. The discovery of neutrino oscillation, confirmed independently by experiments in Japan, Canada, and elsewhere, and later recognized with a shared physics award, definitively proved that neutrinos are not massless after all. This might sound like a minor technical correction, but its consequences ripple through the entire theoretical structure. The Standard Model, as originally constructed, has no mechanism to give neutrinos mass at all. Unlike every other particle, which acquires its mass through interaction with the Higgs field. Explaining neutrino mass requires either extending the theory to include right-handed neutrino partners that have never been directly observed, or invoking an entirely different mechanism called the seesaw mechanism, which connects the extraordinarily small mass of ordinary neutrinos to the existence of extremely heavy, undiscovered partner particles at energies far beyond anything current colliders can reach. Either path requires physics beyond the Standard Model as it currently stands. Neutrino mass, unlike the anomalies described earlier, is not a tentative 3 sigma hint that might evaporate with more data. It is a firmly established experimental fact, confirmed by multiple independent experiments using different neutrino sources and different detection techniques. And it is a fact the Standard Model, in its original form, simply cannot accommodate. Physicists studying neutrinos have continued pushing the measurements further, attempting to determine the actual masses of the 3 neutrino types, which remain unknown even though the differences between them have been measured precisely, and attempting to determine whether neutrinos are their own antiparticles, a property that would have profound consequences for understanding the matter-antimatter asymmetry discussed earlier. Experiments searching for a rare hypothetical process called neutrinoless double beta decay, which could only occur if neutrinos are their own antiparticles, have been running for years without a confirmed detection, continuing to narrow the range of possible neutrino masses and properties without yet delivering the discovery that would settle the question. Neutrino mass stands as perhaps the cleanest and least disputed crack in the Standard Model, a confirmed piece of physics beyond the existing theory, hiding in plain sight inside one of the most abundant and least understood particles in the universe. There is a stranger puzzle still, one that most public discussions of particle physics rarely mention, and it concerns a symmetry that, for reasons nobody understands, appears to be respected far more perfectly than the theory requires. The strong nuclear force, responsible for binding quarks together inside protons and neutrons, is mathematically permitted to violate the same charge parity symmetry discussed earlier in connection with the matter-antimatter imbalance. The equations describing the strong force include a parameter, usually written using the Greek letter theta, that could in principle take any value between 0 and a full circle, and there is no obvious reason within the theory itself for that parameter to be small. If theta had a value anywhere close to what the mathematics naturally allows, the strong force would produce a measurable effect, an electric dipole moment in the neutron, essentially a tiny separation of positive and negative charge within the particle, oriented along its spin axis. Physicists have measured the neutron's electric dipole moment with extraordinary precision across multiple experiments, and found it to be, as far as anyone can tell, exactly 0, smaller than 1 part in 10 billion of what the theory would naturally predict if theta took a typical value. For the strong force to respect this symmetry so precisely, with no known reason for it to do so, is a puzzle physicists call the strong charge parity problem, and it represents another example of the same kind of unnatural fine-tuning that shows up in the Higgs mass discussed at the beginning of this account. The most widely favored solution proposes a new particle, one that has never been detected, called the axion. Named partly as a joke by the physicist who proposed it, after a brand of laundry detergent, because it was invoked to clean up a problem in the equations. The axion would be an extraordinarily light, extraordinarily weakly interacting particle whose presence would naturally force the troublesome theta parameter towards zero without requiring any unexplained coincidence. As an additional and unexpected benefit, axions with the right properties could also account for some or all of the universe's dark matter, connecting this obscure theoretical puzzle to the much larger and more famous mystery discussed earlier. Dedicated experiments around the world have spent decades searching for axions, using extraordinarily sensitive detectors designed to catch the faint signal that would be produced if an axion converted into a photon inside an intense magnetic field. These experiments have steadily ruled out large ranges of possible axion masses and interaction strengths without a confirmed detection. CERN itself hosts one such experiment. Using a decommissioned magnet originally built for a different purpose, repurposed to search for axions that might be streaming continuously from the core of the Sun. So far, none has been found. The strong charge parity problem remains unresolved, a symmetry respected with a precision that the underlying theory offers no explanation for, and the particle proposed to explain it remains, after nearly half a century of searching, entirely hypothetical. Perhaps the strangest crack of all is not a missing particle or an unexplained number, but a question about the stability of the universe itself. And the measurement of the Higgs boson's own mass turns out to sit uncomfortably close to the answer. Once physicists had a precise value for both the Higgs mass and the mass of the heaviest known particle, the top quark, they were able to calculate something called the vacuum stability of the universe, essentially asking whether the state of empty space we currently inhabit represents the lowest possible energy configuration that space can occupy, or whether a lower energy state exists somewhere else in the mathematics, one that the universe could, in principle, eventually fall into. The calculation is delicate, and it depends sensitively on the precise masses involved. But the current best measurements place the universe in an unsettling position, described by physicists using the term metastable. This means our vacuum is not the lowest possible energy state available, but the barrier separating our current state from that lower energy state is high enough, and the process required to cross it improbable enough that the expected time for such a transition to occur is vastly longer than the current age of the universe, longer by a margin so large that the numbers involved lose any intuitive meaning. If a lower energy vacuum state exists, the calculation suggests, purely by chance, a tiny bubble of that lower energy state could someday nucleate somewhere in the universe. And if it did, it would expand outward at nearly the speed of light, converting everything it touched into the new vacuum configuration, an event that would rewrite the rules of physics within that expanding bubble entirely. It is worth being precise about what this means and does not mean. The timescale involved is so vast, and the probability so vanishingly small, that this represents no meaningful concern for anyone living today, or for the next uncountable numbers of generations after them. Physicists who study this calculation are not raising an alarm about an imminent event. What makes the result scientifically significant is not the possibility of catastrophe, but the coincidence embedded in the numbers themselves. The masses of the Higgs boson and the top quark appear to sit almost precisely on the boundary between a universe that would be completely stable forever and one that would have already collapsed into a lower energy state in the earliest fractions of a second after the Big Bang. Nudge either mass by a small percentage in one direction, and the universe would be perfectly stable with no lower energy state ever reachable. Nudge it the other way, and the universe as we know it would never have survived long enough to form a single galaxy. Sitting precisely on that razor's edge, with no theoretical explanation for why the constants of nature happen to balance there rather than anywhere else, is exactly the kind of unexplained fine-tuning that echoes the hierarchy problem discussed earlier, and many physicists suspect the two puzzles are connected, both pointing towards some deeper structure in nature that current theory has not yet uncovered. Refining the measurements of the Higgs and top quark masses remains an active priority at the Large Hadron Collider. Not because anyone expects an immediate answer about the fate of the universe, but because the precise location of that boundary is itself a clue, a number the universe seems to be trying to tell us something with, if only physicists can figure out what. Taken individually, each of these puzzles might be dismissed as a technical curiosity, the kind of unresolved detail that exists in every scientific field and eventually gets folded into a more complete theory. Taken together, a pattern becomes harder to ignore. The mass of the Higgs boson requires an unexplained cancellation of enormous quantum corrections. The strong force respects a symmetry with a precision the equations do not demand. The Higgs and top quark masses sit balanced on the exact boundary between stability and collapse. Neutrinos have mass the original theory cannot produce. Roughly 5 times more matter exists in the universe than the theory accounts for. And the very fact that matter exists at all, rather than annihilating completely with antimatter in the earliest moments after the Big Bang, requires a source of imbalance the theory cannot fully supply. Each of these, on its own, is called a fine-tuning problem or a missing mechanism. Together, they read less like isolated oversights and more like the outline of a larger structure the Standard Model was never built to contain. This is precisely why physicists have taken seriously an idea that sounds, on first hearing, closer to philosophy than physics, the notion that the fine-tuning observed throughout nature might not require a deeper mechanical explanation at all, but might instead reflect a selection effect operating across an enormous number of separate universes. The idea draws support from a branch of theoretical physics called string theory, which, in one of its more startling implications, suggests that the mathematics allows for an almost incomprehensibly large number of distinct possible universes, each with different values for the fundamental constants of nature, different particle masses, different strengths for the forces, potentially different numbers of large spatial dimensions entirely. If something like an eternally inflating multiverse produces vast numbers of such universes, each with its own randomly assigned physical constants, then only a small fraction of them would have constants compatible with the formation of atoms, stars, and eventually observers capable of measuring any of this in the first place. Under this framework, called the anthropic principle when applied to physics, the extraordinary fine-tuning of the Higgs mass, or the near-perfect balance of the vacuum stability calculation, would require no additional explanation beyond the trivial observation that any universe capable of producing someone to ask the question must, by necessity, have constants compatible with that observer's existence. It is an idea that many physicists find deeply unsatisfying, precisely because it offers no way, even in principle, to test it directly, and because it can be invoked to explain away almost any coincidence without further predictive power. Other physicists consider it the most honest current answer available, given that decades of searching for alternative explanations, supersymmetry chief among them, have failed to produce confirming evidence at the energies now accessible to experiment. The tension between these two positions, one holding that a deeper, discoverable mechanism must explain the fine-tuning observed throughout nature, and the other suggesting that no such mechanism exists, and the fine-tuning is simply what any observer would be guaranteed to find, sits at the center of theoretical physics today, and it is not a disagreement that any collider experiment can resolve directly. What the Large Hadron Collider and its companion experiments around the world can do is continue narrowing the possibilities, ruling out entire categories of mechanical explanations one by one, as it has already done for the simplest versions of supersymmetry, and testing whether any of the anomalies described so far strengthens into something undeniable, or fades the way the Diffeton bump and the lepton universality anomaly at low energies both eventually did. Every null result and every persistent anomaly shifts the balance of the argument slightly, even if it cannot settle it outright. The crack in the standard model, whatever its ultimate explanation, is real. What remains unknown is whether it will ever be filled in by an equation, or whether physicists are staring at the edge of something that, by its very nature, has no further explanation to give. None of this has slowed the pace of experimentation. Since 2022, the Large Hadron Collider has been operating in what is called Run 3, colliding protons at the highest energy the machine has ever achieved, and accumulating data at a faster rate than in either of its two previous operating periods. Every one of the anomalies described so far is being re-examined with this new data, and several, including the R(d) measurements and the search for rare decay processes connected to the matter-antimatter imbalance, are expected to reach substantially improved precision within the next few years. Precision that may finally push some of these 3 and 4 sigma hints across the 5 sigma line that separates a persistent curiosity from a confirmed discovery, or alternatively, precision that may finally make them disappear for good. Beyond Run 3, an even larger upgrade is already under construction, called the High Luminosity Large Hadron Collider, scheduled to begin operation in the final years of this decade. The upgrade will not increase the collision energy further, but it will dramatically increase the rate at which collisions occur, allowing the detectors to collect roughly 10 times more data over the following decade than the machine has produced across its entire operating history to date. For anomalies that depend on statistical significance slowly accumulating over years of measurement, this represents the single most important development on the horizon. Processes so rare that only a handful of examples have ever been recorded will suddenly become accessible in the thousands, and searches for extremely subtle deviations from standard model predictions, the kind of deviations that a new but very heavy particle might produce, will become dramatically more sensitive. Looking further ahead, CERN has proposed an even more ambitious successor, a circular collider with a tunnel nearly 4 times longer than the current one, wrapping almost 100 kilometers beneath the same region of France and Switzerland. The proposal, still under review and requiring approval and funding from CERN's member states before construction could begin, would first operate as an extraordinarily precise factory for producing Higgs bosons and other known particles in enormous quantities, refining measurements of exactly the kind that revealed the vacuum stability puzzle discussed earlier, before eventually being upgraded to collide protons at energies roughly 7 times higher than anything achieved today. A machine operating at that energy would directly probe mass ranges where many of the theoretical explanations proposed for the anomalies described throughout this account, from leptoquarks to new, heavier partners of the Higgs boson, predict new particles should finally become directly producible and observable. Whether that machine is ever built lies as much in the realm of political and financial decision-making as it does in physics, requiring sustained international commitment over a construction timeline stretching across decades. What is certain is that the current generation of experiments has not run out of room to search. Every crack described in this account remains open, some narrowing steadily as new data arrives, some persisting stubbornly despite every attempt to resolve them, and at least one, the mass of neutrinos, standing as confirmed fact rather than tentative hint. The coming decade of data collection will not answer every question raised here, but it will very likely determine which of these cracks are illusions, which are genuine signposts toward new physics, and which will simply remain unresolved for another generation of physicists to inherit. Not every anomaly described so far unfolded over years of careful, patient measurement. Some collapse within months, in a manner dramatic enough to serve as a warning about how easily even excellent scientists can be misled by their own instruments. And one particular episode remains a favorite cautionary story told to every new generation of physicists entering the field. In September of 2011, the Opera collaboration, operating a detector in Italy that received a beam of neutrinos fired underground from CERN, roughly 730 kilometers away, announced a result that seemed to violate one of the most secure pillars of modern physics. Their measurements suggested the neutrinos had arrived slightly earlier than light, traveling the same distance through a vacuum would have, implying the particles had traveled faster than the speed of light itself. A result that, if true, would have overturned Einstein's theory of special relativity, a theory confirmed by more than a century of experiments across every branch of physics. The collaboration, to their credit, did not rush to claim a discovery of new physics. They spent months rechecking every part of their measurement before releasing the result publicly, and even then, framed the announcement with unusual caution, explicitly inviting independent scrutiny and further experiments to check the result rather than claiming victory. The scientific and public reaction was nonetheless immediate and enormous. Newspapers around the world ran headlines suggesting Einstein might have been wrong. Physicists at other laboratories began designing experiments specifically to test the claim, using different detectors and different neutrino beams entirely. Theoretical physicists, in the meantime, produced an enormous volume of papers attempting to explain how such a result could be reconciled with everything else known about physics, some proposing exotic new particles or extra dimensions that neutrinos might briefly travel through as a shortcut, others expressing open skepticism that a measurement this consequential could survive close examination. Skepticism proved justified. Within months, the Opera collaboration identified two separate technical problems with their experimental setup. A fiber optic cable connecting a computer to the experiment's timing system had not been fully secured, introducing a small but significant delay in one part of the measurement chain. A separate issue with the oscillator used to timestamp events introduced a further error in the opposite direction. Once both problems were corrected, the anomaly vanished completely. The neutrinos had traveled at the ordinary speed expected for particles moving at very close to, but not exceeding, the speed of light, exactly as relativity demands. The collaboration published a correction. Several of its leaders resigned their positions in the aftermath. And the episode became a defining lesson in experimental physics about the danger of publicizing an extraordinary claim before every possible source of systematic error has been exhaustively ruled out. The story is worth telling alongside every other anomaly in this account, not because it undermines the credibility of the anomalies still under active investigation, but because it illustrates precisely why physicists insist on such an extraordinarily high bar of evidence before declaring a genuine discovery. A loose cable connection produced a result that appeared, on its face, to overturn more than a century of settled physics. It took the collaboration's own rigor and the willingness of the broader scientific community to demand independent verification rather than simply accepting a headline-grabbing announcement to reveal the true, mundane explanation hiding behind an extraordinary claim. Every anomaly discussed throughout this account, from the lepton universality measurements to the W boson mass discrepancy, is being subjected to exactly this same level of scrutiny, precisely because the field has learned, through episodes like this one, how costly it is to celebrate a crack in reality before confirming that the crack is not simply a loose cable somewhere in the instrument. The standard physicists use for declaring a genuine discovery 5 standard deviations, corresponding to odds against a chance fluctuation of roughly 1 in 3.5 million, was not chosen arbitrarily. It reflects hard-learned experience from decades of searches across many different subfields, during which weaker thresholds repeatedly produced false alarms that consumed years of theoretical attention before dissolving under closer examination. The diphoton bump discussed earlier never crossed that threshold, and its collapse validated the caution embedded in the standard. The Opera result was, in a sense, worse than a statistical fluctuation, since the collaboration's stated significance was extremely high, yet the entire result traced back to a hardware fault rather than any property of nature at all. A reminder that even overwhelming statistical confidence cannot protect against an error hiding somewhere in the measurement chain itself, invisible until someone finds it. This is why the anomalies still under active investigation, the persistent R sub d deviation, the unresolved CDF-W boson mass discrepancy, the 3 standard deviation, split between competing theoretical calculations of the muon's magnetic moment, are treated with a particular kind of professional patience that can look, from the outside, almost like indifference. Physicists working on these measurements do not celebrate prematurely because they have watched, within their own careers, results that seemed just as compelling evaporate entirely. At the same time, they do not dismiss these anomalies either, because the field has also witnessed real discoveries emerge from exactly this kind of a slow accumulation of evidence, the Higgs boson itself among them, confirmed only after decades of theoretical prediction and years of increasingly precise experimental searching that gradually excluded every alternative explanation until only the true signal remained, standing, living inside this uncertainty, for years or decades at a time, without knowing whether a measurement will resolve into history's next great discovery or its next great false alarm, requires a particular kind of discipline that outsiders sometimes find difficult to understand. It means committing enormous resources, years of a research career, vast computing power, and in some cases, the collective effort of thousands of collaborators spread across dozens of countries, toward questions that may ultimately answer themselves with nothing more dramatic than a confirmation of theories already well understood. It also means remaining alert enough and rigorous enough to recognize the signal if one ever does appear clearly enough to survive every possible test thrown against it. This tension between healthy skepticism and genuine openness to discovery is not a flaw in how modern physics operates. It is the entire mechanism by which the field has managed, again and again, to distinguish real cracks in its understanding from illusions produced by chance, faulty cables, or wishful interpretation of ambiguous data. Understanding why any of these anomalies took years to even become visible requires understanding the sheer scale of the search itself. Inside the Large Hadron Collider, proton bunches cross each other roughly 40 million times every single second, and each crossing can produce dozens of separate collisions simultaneously, each collision scattering hundreds of new particles outward through the detector in every direction. The resulting flood of information, if recorded in full, would amount to something on the order of 1 million terabytes of data every second, an amount so large that no storage system on the planet could keep pace with it, and no computer could ever hope to sift through it afterward looking for anything meaningful. Instead, each detector relies on an extraordinarily fast filtering system called a trigger, essentially a layered set of automated decisions made in real time, within millionths of a second, that determine whether a given collision is interesting enough to keep or should be discarded permanently before it is ever fully recorded. The first layer of this filtering happens directly on specialized processing hardware built into the detector itself, making a preliminary judgment based on rough features of the event, such as whether an unusually high-energy particle appeared somewhere in the detector. Events that pass this first filter, still numbering in the tens of thousands per second, are passed to a farm of ordinary computers that perform a faster, simplified reconstruction of the event, deciding within a few thousandths of a second whether to keep it for full analysis. Only a tiny fraction of all collisions, roughly 1 in 100,000, ultimately survives this cascade of decisions to be permanently recorded and studied by physicists. Every anomaly described throughout this account exists somewhere within that recorded fraction, buried among billions of ordinary, uninteresting collisions that look almost identical to the rare, meaningful ones physicists are actually searching for. Finding a handful of beauty quark decays, exhibiting a subtle deviation from a predicted ratio, or isolating the small number of tau lepton decays needed to measure R sub d with any precision, means combing through datasets containing trillions of recorded collisions, most of which have absolutely nothing to do with the process being studied, using statistical techniques refined over decades specifically to separate a faint, genuine signal from an overwhelming background of ordinary physics that mimics it in almost every superficial respect. The computing infrastructure required to store and analyze this data is itself a global collaboration, a distributed network linking hundreds of computing centers across dozens of countries, sharing the processing burden because no single institution, however large, could handle the analysis alone. This scale is worth appreciating on its own terms, independent of whichever anomaly eventually proves real. Every measurement described throughout this account, whether it ultimately vanishes like the Diffeton bump or persists like the R sub d deviation, represents the successful extraction of an extraordinarily faint signal from a genuinely overwhelming amount of noise, achieved through engineering and statistical methods that did not exist a generation ago. The fact that physicists can detect a 3-standard deviation in a ratio of particle decays occurring perhaps a few thousand times across an entire decade of operation, buried among quadrillions of ordinary collisions, is itself one of the most remarkable achievements in the history of experimental science, regardless of what any individual anomaly ultimately turns out to mean. Behind every measurement described in this account stands a workforce whose scale rivals that of the machine itself. The ATLAS and CMS collaborations each include several thousand physicists, engineers, and students, drawn from hundreds of universities and research institutes spread across dozens of countries, many of whom will never meet each other in person despite spending years working on the same analysis. LHCb, though smaller, still draws its membership from institutions scattered across every continent except Antarctica. A single published measurement, such as the final R sub k result that closed the lepton universality anomaly, typically represents years of effort from hundreds of contributors, including the people who built and maintain the detector hardware, the people who write and validate the software used to reconstruct particle trajectories from raw electronic signals, the statisticians who develop the methods used to separate signal from background, and the theorists working elsewhere who calculate the precise standard model predictions the measurement is ultimately compared against. This collaborative structure exists for reasons that go beyond simple scale. No single national government, and in the current geopolitical landscape, quite possibly no single group of governments, could fund a machine of this size and complexity alone. Nor could any single institution supply the enormous breadth of expertise required, spanning cryogenic engineering, superconducting magnet design, radiation-resistant electronics, distributed computing, and theoretical physics, all at the frontier of their respective fields simultaneously. CERN itself was founded in the aftermath of the Second World War specifically as an instrument of scientific cooperation between nations that had, within living memory, been at war with each other, built on the explicit premise that fundamental research could serve as common ground even when political relationships elsewhere remained strained. Physicists working on these experiments today still describe that founding principle as something they experience directly in their daily work. Sitting in meetings alongside colleagues from nations with sharply different governments and sharply different relationships with each other outside the walls of the laboratory. It is worth pausing on the fact that thousands of people have devoted entire careers, in some cases entire working lives, to measurements whose outcome could plausibly be nothing more dramatic than a confirmation of a theory already understood in its broad outlines for half a century. The physicist who spent a decade helping refine the R sub k measurement, only to watch the anomaly it once suggested dissolve into agreement with the standard model, did not waste that decade. The measurement itself, regardless of its outcome, sharpened humanity's understanding of exactly how precisely nature obeys, or fails to obey, one of its most fundamental symmetries, and that sharpened understanding becomes the foundation on which the next generation of searches is built. Every ruled-out possibility narrows the space in which a genuine discovery could still be hiding, and narrowing that space, patiently and honestly, year after year, is itself the substance of the work, whether or not any individual measurement ever makes headlines. One further pattern deserves mention, precisely because it remains more contested among physicists than any of the anomalies described so far, and because it illustrates how a genuine crack might first appear, not as a single clean measurement, but as a scattered collection of small excesses across many different, seemingly unrelated searches. Since the middle of the 2010s, a relatively small number of researchers working with both the ATLAS and CMS detectors have pointed to a cluster of modest excesses appearing across several different final states. Events containing 3 or 4 leptons, subtle enhancements in the production of pairs of the particles that carry the weak force, and small deviations in certain measurements involving the heaviest known particle, the top quark. None of these individual excesses reaches a significance anywhere close to the 5 sigma threshold required for discovery, and several, taken in isolation, are well within the range expected from ordinary statistical fluctuation. What has kept a subset of theorists interested is the observation that if a new, relatively light particle existed, potentially a second Higgs, like scalar with a mass somewhat below that of the known Higgs boson, its predicted decay signatures would touch several of these otherwise unconnected excesses simultaneously, providing a single unifying explanation for a pattern spread across measurements that were never designed to be analyzed together. Researchers who advocate taking this pattern seriously have published detailed phenomenological studies proposing specific extended theories involving additional scalar particles beyond the single Higgs boson, confirmed in 2012, capable of producing exactly this scattered constellation of small effects. Other physicists in the field remain openly skeptical, pointing out that examining enough different final states across enough different analyses will inevitably produce a handful of excesses purely by chance, and that a pattern assembled after the fact from measurements originally designed for entirely different purposes carries much weaker evidential weight than a single anomaly predicted in advance, and then confirmed. This disagreement is itself instructive because it shows the anomaly hunting process at an earlier and messier stage than the cleaner stories told earlier in this account. The lepton universality measurements and the R sub d anomaly each involved a single, well-defined quantity, measured the same way by multiple independent experiments, which makes comparison and combination relatively straightforward. The multi-lepton pattern, by contrast, involves stitching together excesses from analyses using different selection criteria, different background estimation techniques, and different detectors, a process considerably more prone to the kind of unintentional cherry-picking that produced the false diphoton bump years earlier. Recent, dedicated searches specifically designed to test for a new light scalar particle using machine learning techniques to hunt broadly across many possible final states at once have so far reported no significant excess above standard model expectations, a result that tempers, without entirely eliminating, the case for taking the original scattered pattern seriously. Whether this particular thread eventually resolves into a confirmed discovery, fades away like the diphoton bump before it, or simply remains a permanent minority position within the field, unresolved and unconvincing to most, but never definitively excluded. It captures something important about how science actually proceeds at its uncertain edges. Not every crack announces itself cleanly. Some begin as a handful of physicists, noticing that several unrelated measurements seem to be leaning in the same direction, then spending years building the case, refining the theory, and waiting for the data that could either confirm or finally close the question. Most such patterns turn out to be nothing. A small number, throughout the history of the field, have turned out to be the first hint of something real. Step back from any single measurement, and a shape begins to emerge from everything gathered so far. The Higgs boson exists exactly where theory said it would, yet its mass depends on a cancellation so precise that nothing in the equations explains why it happens. Supersymmetry, the leading candidate for explaining that cancellation, has been searched for relentlessly and has not been found anywhere within reach of current energies. A bump that once looked like an entirely new particle turned out to be nothing, dissolving the moment enough data arrived to test it properly. A years-long deviation in how beauty quarks decay into electrons versus muons followed the same arc, tantalizing for the better part of a decade before finally settling into agreement with the theory that predicted it should. A closely related deviation, involving the far heavier tau lepton instead, has refused to follow that same arc, persisting essentially unchanged across nearly 10 years of independent measurements from separate experiments on separate continents. A long-standing tension in the muon's magnetic moment was resolved, not by any new experimental result, but by revising the theoretical calculation it was being compared against, a resolution that quietly opened up a new disagreement between two competing theoretical methods that remains unsettled today. A single measurement of the W boson's mass continues to disagree with every other measurement of the same quantity by an enormous margin, defended by the collaboration that produced it and unconfirmed by anyone else 4 years on. Beneath all of these individual threads sit questions the standard model has never claimed to answer at all. Neutrinos carry mass the original theory cannot produce, a fact confirmed beyond any reasonable doubt. Roughly 5 times more matter exists in the universe than the theory accounts for, detected only through its gravitational influence, and never once produced directly in any collider search, despite years of dedicated effort. The strong force respects a symmetry more precisely than any known mechanism requires it to. And the very fact that any matter survived the earliest moments after the Big Bang, rather than annihilating completely against its antimatter counterpart, depends on an imbalance the theory can supply only a tiny fraction of, layered on top of everything else. The measured masses of the Higgs boson and the heaviest known particle happen to sit almost exactly on the narrow boundary between a universe that would remain stable forever and one that should already have collapsed into a different configuration entirely. None of these threads, examined individually, constitutes a confirmed discovery of new physics. Several have already been tested and found to agree, after all, with the theory as it currently stands. But taken together, they describe a theory that works with extraordinary precision everywhere it has been tested, while resting on a foundation riddled with unexplained numbers, missing mechanisms, and persistent, unresolved tensions that refuse either to strengthen decisively or to disappear entirely. This is, in the end, the real meaning behind the idea of a crack in reality. Not a literal fracture in the fabric of space, and not evidence that the universe is somehow breaking down. It is a crack in the completeness of the best description of nature humanity has ever built, a description that predicts the outcome of experiments to more decimal places than almost any other theory in the history of science, while simultaneously admitting, through every anomaly recounted here, that it cannot yet explain why the numbers inside it take the values they do. It is worth asking directly, what would actually change if one of these persistent cracks were finally confirmed, rather than resolved away like so many before it? A confirmed violation of lepton universality in tau. Lepton decays, for instance, crossing the 5 sigma threshold, with data still to come from Bell 2 and the ongoing runs at CERN, would mean the electron, the muon, and the tau. 3 particles the Standard Model treats as identical twins, differing only in mass, are not actually treated identically by nature after all. It would imply the existence of an entirely new force or a new category of particle, likely at an energy within reach of the current or next generation of colliders, providing physicists with an actual target to search for directly, rather than a statistical hint to keep chasing. Theorists have already sketched out what such particles might look like, and confirming their existence would represent the first fundamentally new addition to humanity's picture of nature's building blocks since the neutrino oscillation discoveries at the turn of the millennium. A confirmed resolution of the W boson mass discrepancy, in whichever direction it eventually falls, would carry similarly large consequences. Should the CDF measurement eventually be vindicated by some future experiment achieving comparable precision, it would represent one of the largest deviations from Standard Model predictions ever confirmed in the history of particle physics, all but guaranteeing the existence of new particles or interactions within reach of upcoming experiments. Should it instead be traced to some subtle, currently unidentified systematic error, as several physicists suspect but none has yet definitively demonstrated, it would still stand as an instructive case study in how even the most careful, most experienced experimental teams can occasionally arrive at a result the rest of nature simply does not confirm. Perhaps the most consequential possibility of all involves dark matter, precisely because a confirmed detection would not remain a curiosity confined to academic journals. Understanding what dark matter actually consists of would immediately answer one of the oldest open questions in astrophysics, explaining the invisible scaffolding that holds galaxies together and shaped the large-scale structure of the entire observable universe. It could also, depending on the specific properties of whatever particle is eventually found, open entirely new avenues of technology, in the same way that earlier fundamental discoveries in particle physics originally pursued purely out of curiosity about the basic structure of matter, eventually gave rise to medical imaging technologies, semiconductor manufacturing techniques, and the particle accelerators now used daily in hospitals to treat cancer patients around the world, none of which were the original goal of the research that produced the underlying discoveries. This is, in fact, the quiet argument for continuing to fund and build ever larger and more sensitive instruments, even when so many searches, year after year, return null results. The history of fundamental physics research offers few reliable ways to predict in advance which line of curiosity-driven inquiry will eventually produce something of immense practical value, and offers many examples of profound applications emerging decades after the original research seemed, at the time, to have no obvious use at all. Whether or not any of the specific anomalies described throughout this account eventually resolves into a confirmed discovery, the instruments, computational techniques, and collaborative networks built to chase them continue accumulating capabilities that ripple outward into fields far beyond particle physics itself, long before anyone can say for certain whether the crack being chased was ever real. CERN's own history offers a fitting illustration of exactly this pattern, since some of its most consequential contributions to the wider world emerged as almost accidental byproducts of an entirely different pursuit. In the late 1980s, a researcher at the laboratory needed a way for physicists scattered across dozens of institutions and countries to share documents and data about ongoing experiments without each collaborator needing specialized software or compatible computer systems. The solution he proposed, a system of linked documents accessible through a simple universal protocol, was published internally with modest expectations, intended purely to solve an administrative headache within one physics laboratory. That system became the World Wide Web, released freely to the public a few years later, with no patent and no licensing fee attached. A decision that allowed it to spread globally and eventually reshape nearly every aspect of modern life, from commerce to communication, to the very existence of the platform through which this account is likely being watched. The particle detectors themselves have followed a similar trajectory. Techniques originally developed purely to track the paths of subatomic particles through a detector with extraordinary precision were later adapted into medical imaging systems capable of visualizing tumors and other tissue abnormalities with far greater clarity than earlier technology allowed. The particle accelerators built to explore fundamental physics questions inspired smaller, purpose-built versions now used routinely in hospitals to deliver precisely targeted radiation therapy to cancer patients, sparing surrounding healthy tissue in ways earlier treatment methods could not achieve. None of these applications were the goal when the underlying research began. Each emerged because physicists, chasing questions with no guaranteed practical payoff, developed tools sensitive and precise enough to solve problems nobody had originally set out to solve. This history matters for understanding the anomalies described throughout this account, because it reframes what might otherwise look like a frustrating pattern of anomalies rising and then dissolving, one after another, over more than a decade of searching. Even the null results carry value beyond the narrow question of whether a specific particle exists. Every improvement in detector sensitivity required to rule out a proposed dark matter candidate, every refinement in statistical technique developed to distinguish a genuine 3 sigma signal from an ordinary background fluctuation, every advance in distributed computing infrastructure built to process the flood of data pouring out of the collider becomes a permanent addition to humanity's toolkit, available for whatever the next generation of scientists, in particle physics or in some entirely unrelated field, eventually needs it for. The crack in the standard model may or may not ever be filled in with a confirmed new particle. The instruments built to search for it are already reshaping the world in ways nobody fully anticipated when construction on the tunnel outside Geneva first began. There is a deeper reason this kind of search continues to draw so many people into it, one that has little to do with any specific technological payoff and everything to do with a much older impulse. Long before anyone understood atoms, quarks, or quantum fields, human beings looked at patterns in the world around them and asked why those patterns existed, rather than some other arrangement entirely. The same curiosity that once drove early astronomers to track the wandering motion of planets against a backdrop of seemingly fixed stars, centuries before anyone understood gravity well enough to explain what they were seeing, now drives physicists to track infinitesimally rare particle decays through a detector buried beneath the countryside, hunting for a pattern that might reveal something about the deepest structure of existence. What makes the current moment in particle physics feel distinct from earlier eras of discovery is the sheer scale of confidence the Standard Model has earned through decades of successful prediction, paired with an equally striking awareness among the very physicists who built and confirmed that theory of how much it still cannot explain. There have been other moments in the history of physics when a well-established theory appeared essentially complete, only for a small, seemingly minor discrepancy to eventually unravel the entire framework and reveal something far stranger underneath. The tiny, unexplained wobble in the orbit of Mercury, dismissed for decades as a minor irregularity, eventually became one of the first confirmed pieces of evidence for general relativity. An entirely new theory of gravity that replaced Newton's after more than 2 centuries of essentially unchallenged success. A faint, unexplained hiss picked up by a radio antenna in New Jersey in the 1960s, initially suspected to be caused by pigeon droppings inside the equipment, turned out to be the afterglow of the Big Bang itself, confirming an entire cosmological framework almost by accident. Nobody can say with confidence whether any of the anomalies described throughout this account will follow that same path, growing from a minor irregularity into the foundation of an entirely new understanding of nature. Most historical anomalies, it is worth remembering honestly, do not. Most turn out to be loose cables, statistical noise, or subtle errors in an otherwise sound calculation. And the physicists chasing them absorb that outcome as simply part of the process, moving on to the next question with the same rigor they applied to the last. But the possibility that one of them will not fade, that one of these cracks will instead widen into an entirely new chapter of physics, is precisely what continues to justify building bigger detectors, collecting more data, and refining calculations that have already taken decades to reach their current level of precision. It is the same impulse that first sent astronomers outward with telescopes centuries ago, applied now to structures so small that no telescope could ever see them directly, requiring instead a machine capable of recreating, for a fraction of an instant, energy conditions that have not existed naturally anywhere in the universe since a tiny fraction of a second after everything began. As of today, every thread described throughout this account remains genuinely open, actively being measured, refined, and argued over inside collaboration meetings and physics conferences happening this very year. Run 3 of the Large Hadron Collider continues collecting collisions at record energy, and both ATLAS and CMS are steadily working through data sets that will eventually surpass everything collected during the machine's first decade of operation combined. LHCb, having closed the low-energy lepton universality anomaly conclusively, has shifted its full attention toward sharpening the R sub d measurement, along with dozens of other tests of charge, parity violation, searching for the missing source of matter, antimatter asymmetry. Bell 2 in Japan continues accumulating its own independent sample of tau lepton decays, providing a crucial cross-check using an entirely different type of particle collision than anything produced at CERN. The muon G-2 theory initiative continues working to reconcile its two competing calculation methods. Aware that the next word on the subject may reopen a question many outside the field now consider closed, and the working group tasked with reconciling the W boson mass measurements continues meeting, still without a resolution that satisfies every collaboration involved. None of these efforts pauses to wait for headlines, and most of the incremental progress being made will never reach public attention at all, appearing instead as a slightly narrower uncertainty band in an academic paper or a conference slide updating a number by a fraction of a standard deviation. This is what genuine scientific progress actually looks like from the inside, patient, incremental, and almost entirely invisible to anyone not following the specific measurement closely, punctuated only rarely by a result significant enough to draw wider attention, as the original Higgs discovery did in 2012, or as a confirmed 5 sigma detection of new physics would do, whenever and if it finally arrives. Construction on the proposed successor collider, still awaiting final approval from CERN's member states, would not begin producing results for at least another 2 decades, even under an optimistic timeline, meaning many of today's graduate students will spend their entire careers working toward experiments that current researchers may never see completed. And yet the field continues, driven by the same combination of patient rigor and genuine curiosity that carried it from an initial theoretical prediction in the 1960s, through half a century of indirect evidence, to a definitive discovery in a tunnel outside Geneva in 2012. And now into a new era spent probing the edges of that same theory for whatever remains hidden just beyond its reach. The crack described throughout this account has not closed. It has not widened into an undeniable new discovery either. It sits exactly where it has sat for over a decade, being measured with ever greater precision by thousands of people who understand, better than almost anyone else, just how easily a crack like this can turn out to be nothing at all, and just how much would change if it turned out to be real. There is one final thread worth pulling before closing, because it reframes everything described so far in a way that is easy to miss while moving quickly from one anomaly to the next. Every single measurement recounted throughout this account, whether it ultimately dissolved into agreement with the standard model or continues to resist explanation today, was made possible only because human beings built a machine capable of recreating, for an instant smaller than any unit of time most people ever consider, conditions that last existed naturally across the entire universe, a tiny fraction of a second after everything began. The protons colliding inside that 27-kilometer ring reach energies that briefly recreate a version of the universe as it existed before atoms could form, before protons and neutrons themselves had even settled into stable existence, when the 4 fundamental forces, now clearly distinguishable from one another, may have behaved as a single, unified force instead. Seen from this angle, every anomaly described throughout this account, the persistent tau lepton anomaly, the unresolved W boson mass, the missing dark matter particle, the imbalance between matter and antimatter, represents a question being asked directly of the conditions that gave rise to the universe itself, using a machine built specifically to briefly recreate a sliver of those conditions here on the surface of a planet orbiting an ordinary star in an ordinary galaxy, roughly 13.8 billion years after everything began. The physicists spending their careers chasing these cracks are not simply solving abstract mathematical puzzles disconnected from anything larger. They are asking the universe, directly and repeatedly, to reveal a little more about the rules it was built under in the earliest and strangest moments of its own existence. Moments that left behind exactly the kind of subtle, hard-to-detect fingerprints described throughout every anomaly recounted here. It remains entirely possible that every open crack described in this account eventually resolves quietly into agreement with the theory already in hand. Following the path of the Diffeton bump, the low-energy lepton universality anomaly, and the opera neutrino result before them, each of which seemed, for a time, like it might rewrite the rules of physics before dissolving under closer examination. It is equally possible that one or more of them, the persistent tau lepton deviation, the isolated W boson mass discrepancy, the still unexplained absence of any confirmed dark matter particle despite years of dedicated searching, represents the genuine first thread of a discovery that will eventually stand alongside the confirmation of the Higgs boson as one of the defining moments in the history of this field. Nobody currently knows which outcome awaits, and that uncertainty, rather than being a weakness in how physics operates, is the entire reason the search continues with such patience and such care. The Standard Model remains, by any reasonable measure, one of the most successful theories human beings have ever constructed. Tested across more than half a century of experiments and confirmed to a level of precision matched by almost nothing else in science. And it remains, simultaneously, a theory riddled with unexplained numbers, missing mechanisms, and persistent tensions that refuse to fully resolve, sitting exactly where they have sat for years, watched closely by thousands of researchers scattered across the planet, waiting to see whether the next dataset finally closes the question or deepens it further. Somewhere inside that unresolved tension between extraordinary success and stubborn incompleteness sits whatever comes next in humanity's understanding of the universe. Hidden inside collisions occurring 40 million times each second, in a tunnel beneath the border of two countries, built by people who understood from the very beginning that the most interesting answer a machine like this could ever provide was not a confirmation of everything already known, but a crack, however small, in the reality they thought they understood. It is worth addressing directly the most common objection raised by skeptics of any individual anomaly described throughout this account, because it is a fair objection and deserves a fair answer rather than a dismissal. Skilled statisticians point out, correctly, that when thousands of independent measurements are performed across a field as large as particle physics, some fraction of them will inevitably land at 3 or even 4 standard deviations from the true value, purely by chance, simply as a mathematical consequence of how many separate tests are being run simultaneously across hundreds of research groups. This is sometimes called the look elsewhere effect, and it is precisely the reason the 5 sigma threshold exists at such an extreme level of statistical confidence in the first place, chosen specifically to account for the enormous number of opportunities the field has, collectively, to stumble upon an impressive-looking fluctuation that means nothing at all. The honest response to this objection is not to dismiss it, but to distinguish between anomalies that are vulnerable to it and anomalies that are not. The multi-lepton pattern discussed earlier, assembled after the fact from a scattered collection of measurements never designed to be combined, is precisely the kind of result most vulnerable to this criticism. And even researchers sympathetic to taking it seriously acknowledge the difficulty directly. The R sub d measurements are considerably less vulnerable because they involve the same well-defined quantity, predicted in advance by the same well-established standard model calculation, measured independently by 4 separate experimental collaborations using different detectors, different beam types, and different analysis techniques, all landing on the same side of the theoretical prediction rather than scattering randomly around it as a true statistical fluctuation should. The CDFW boson mass measurement occupies its own unusual category entirely, not vulnerable to the look elsewhere effect in the traditional sense, since it involves a single, specific, predefined quantity rather than a search across many possible signatures, but vulnerable instead to the possibility of an undiscovered systematic error specific to that one experimental apparatus, a different and in some ways more difficult problem to rule out definitively. This distinction between anomalies vulnerable to statistical look elsewhere effects and anomalies vulnerable to potential systematic errors in a single measurement is exactly the kind of careful reasoning that separates responsible scientific skepticism from either credulous excitement or reflexive dismissal. Physicists who study these anomalies professionally spend as much of their effort trying to break their own results as they do trying to confirm them, deliberately searching for overlooked sources of bias, alternative explanations within the standard model that could account for an apparent deviation without requiring new physics, and independent cross-checks capable of exposing an error before it misleads the wider field. The R sub D collaboration, the CDF team, and the muon G-2 theory initiative have each published extensive technical discussions addressing precisely these kinds of concerns, not because they were forced to by external pressure, but because this adversarial self-scrutiny is built into how the field evaluates its own results before anyone else is asked to take them seriously. What emerges from this scrutiny is not certainty in either direction, but a carefully graded landscape of confidence, with some anomalies, like the original diphoton bump, essentially ruled out after further data arrived. Others, like the tau-lepton deviation, sitting in a genuinely uncertain middle ground that additional years of data collection may finally resolve one way or the other, and still others, like the confirmed existence of neutrino mass, standing as settled fact, requiring no further debate about whether the effect is real, only about which specific mechanism explains it. Understanding this landscape, rather than collapsing every anomaly into a single undifferentiated category of either confirmed discovery or dismissed noise, is what allows the field to move forward honestly, neither overselling a tentative hint as more certain than it is, nor discarding a genuinely persistent pattern simply because so many earlier patterns turned out to mean nothing. One measurement currently underway ties several of these threads together more directly than almost anything else described so far, because it aims to test the shape of the Higgs field itself, rather than simply the mass of the particle associated with it. The Higgs field is often described using the metaphor of a valley, a landscape of potential energy in which the universe settled, in its earliest moments, into a particular stable configuration, rather than remaining at the featureless peak that existed before the field acquired its present value. The exact shape of that valley, how steep its walls are, and whether it contains a hidden second, deeper valley elsewhere, determines both the vacuum stability question discussed earlier and, more fundamentally, why particles have the specific masses they do. Measuring the mass of the Higgs boson alone reveals only the curvature of the valley floor at the single point the universe currently occupies. To map the actual shape of the surrounding landscape, physicists need to observe events in which two Higgs bosons are produced simultaneously from a single collision, an exceptionally rare process that depends directly on how the field interacts with itself. A property called the Higgs self-coupling. According to the standard model, this process should occur in only about 1 in every 50,000 proton collisions capable of producing a single Higgs boson, making it one of the rarest, measurable processes the Large Hadron Collider has ever attempted to study, and one that has not yet been observed with enough events to draw a definitive conclusion. Both ATLAS and CMS have spent years developing dedicated search strategies for this process, and while neither has yet accumulated enough data to claim a confirmed observation, both have begun placing increasingly tight constraints on how far the Higgs self-coupling can deviate from its predicted standard model value. Early results have already ruled out some of the more extreme deviations that certain theories, including some models proposed specifically to explain the vacuum metastability discussed earlier, would have required. The high luminosity upgrade, currently under construction, is expected to finally provide enough collisions to observe this process directly for the first time, giving physicists their first genuine look at the actual shape of the valley. The universe has been sitting inside since a fraction of a second after the Big Bang, rather than simply its curvature at a single measured point. This measurement carries stakes that extend well beyond a technical curiosity about a rare particle process. If the self-coupling is found to differ meaningfully from the standard model prediction, it would represent direct evidence that the Higgs field is not the simple, single valley the current theory assumes, potentially pointing toward the existence of an entirely new sector of particles interacting with the Higgs in ways not yet incorporated into any existing model, and potentially reshaping the vacuum stability calculation described earlier in ways that could shift the universe from a metastable configuration into either a genuinely stable one or a considerably more precarious one. Should the measurement instead confirm the standard model prediction precisely, it would close off an entire category of proposed theories in one stroke, narrowing the search for new physics even further at a moment when so many other avenues have already come back empty. Either outcome would mark one of the most significant results the Large Hadron Collider has produced since the original discovery of the Higgs boson itself. And unlike several of the anomalies described earlier, this is not a question of statistical chance resolving itself with more data. It is a direct measurement of the actual shape of the field responsible for giving mass to nearly everything in the universe. A measurement that, for the first time, is finally within technical reach. It is tempting, after tracing so many threads across so many years of measurement, to wonder whether physicists themselves ever feel the weight of how long some of these questions have remained open. The hierarchy problem discussed at the very beginning of this account has sat unresolved since long before the Higgs boson was even confirmed to exist, predating the careers of many researchers currently working to solve it. The strong charge parity problem has waited even longer, close to half a century, for an axion or any alternative explanation to finally be detected. Physicists who have spent decades on these questions describe a particular kind of patience required to remain engaged with a puzzle this old, one built not on the expectation of an imminent breakthrough, but on the conviction that steady, careful, incremental progress, even when it produces mostly null results, is the only reliable path toward eventually understanding something this deep about nature. There is also a quieter satisfaction embedded in the process itself, one that has little to do with whether any particular anomaly ever resolves into a confirmed discovery. Each null result, each tightened constraint, each ruled-out region of possible particle masses represents a genuine addition to human knowledge, a small but permanent narrowing of the space in which nature's remaining secrets could still be hiding. The physicist who spends a career searching for supersymmetric particles that are never found has still contributed something real, definitively excluding entire categories of theories that an earlier generation considered among the most promising explanations available, clearing the way for whatever the next generation of ideas turns out to be. In a field this old, and this precisely quantified, even the absence of a discovery becomes data, shaping the next question as surely as a positive result would have. This is, in the end, what it means to search for a crack in the most successful theory ever built about the fundamental workings of nature. It means accepting that most searches will end in agreement rather than revelation, that most 3 sigma hints will fade rather than strengthen, and that even a confirmed discovery, when it finally comes, may take the form of a small, technical deviation in a ratio of particle decays rather than anything as dramatic as popular imagination often expects. And it means continuing anyway, refining the instruments, sharpening the calculations, and returning year after year to the same fundamental questions, because the alternative, simply assuming the standard model must be complete despite everything it cannot explain, has never once been how any of humanity's deepest understanding of nature was actually reached. There is a final image worth holding on to once all of these threads have been laid out side by side, because it captures something the individual measurements, taken one at a time, tend to obscure. Somewhere beneath the fields and villages along the border of France and Switzerland, protons are colliding at this very moment, roughly 40 million times every second. Each collision briefly recreating conditions that last existed naturally across the entire universe in the first instance after everything began. Detectors the size of apartment buildings are recording the debris from those collisions in real time, filtering it, storing it, and passing it along to a distributed network of computers spanning dozens of countries, all so that a small fraction of those events, the ones carrying a beauty quark decaying in an unexpected ratio, or a W boson with a mass that refuses to match its counterparts, or perhaps, eventually, something entirely new that nobody has predicted at all, can be pulled out of that flood and examined closely enough to matter. None of this activity pauses. It has not paused since the machine first switched on, and it will not pause while the questions raised throughout this account remain unresolved. Every anomaly described here, whether it eventually dissolves quietly into agreement or hardens into the next confirmed addition to human knowledge, exists because thousands of people decided, and continue deciding, that understanding precisely why the universe took the shape it did, in the first immeasurably brief fraction of a second after it began, is worth the decades of patient, careful, often unglamorous work required to chase it down. The standard model may yet prove complete in every way that matters, its remaining tensions eventually explained by subtle effects nobody has fully worked out yet. Or it may be standing, right now, on the edge of a discovery that reshapes how every future generation understands the material substance of reality itself. Nobody currently knows which. That uncertainty, chased with this much patience by this many people for this long, is itself one of the more remarkable things happening anywhere on the planet today. Before we go, be sure to like the video and subscribe for more journeys into the cosmos. The crack found beneath Geneva has not closed, and for now, it does not need to.